All right, so thank you, Brad. So as you probably have seen already, I'm the Chief Technology Officer at Crunchy Data. I'm a committer, major contributor, worked on role-level security, column-level privileges, the role system, and other things. So finding slow queries. There's a few different ways to find slow queries in Postgres. Right? The first one I'm going to talk about is through enabling logging configuration, principally through postgresql.conf. And then that's going to also lead into doing log file analysis using one of my favorite tools, PGBadger. And then we're also going to look at viewing active queries. This is primarily going to be using pgstat statements. Of course, as I go through this, please feel free to ask questions, and I'll do my best to answer them as we go through. And then, after we've talked a little bit about how to find and identify the slow queries in your system, we'll talk through some of the different ideas about how you can go about trying to improve the situation and make those queries a little bit faster. We'll cover some kind of common things that I've seen. This is somewhat of an introduction, but happy to answer questions, and we can talk about more sophisticated things if folks are interested. So first and foremost, when it comes to logging, there's a bunch of different configurations in postgresql.conf that are relevant here. And I'm going to kind of go through and talk about these different ones, but logmin duration statement, logline prefix. We'll talk about checkpoints. Checkpoints are actually pretty important. Lock weights, this is a really important one. If you haven't dealt with locking, then you're lucky, because in my experience, that's a common reason why queries end up being slow, is because of actually locking and blocking with other queries and other activity on the system. Temp files can sometimes be an indication of poorly performing queries, so we'll look at that. And we'll talk a little bit about auto vacuum. So logmin duration statement is pretty straightforward. You set it to a number. Right here, I'm setting it to 0, which will actually log every single statement that's sent to the database server. The number that you can configure here is the number in milliseconds of any query that takes longer than this amount of time will be logged. And it's important to use logmin duration statement because that's going to give you the actual duration and the query on the same line, which is a lot easier for log parsing and things like that. There is another approach where you can use log statement and log duration, but that ends up logging them on two different lines. It puts the duration on a separate line from the actual statement, and that's kind of a pain in the butt. So that's why I don't recommend that approach. So here's an example of what that looks like. So here is a select PG sleep of 1, which tells Postgres just to sleep for 1 second-ish. Here you can see that the duration of that ended up being 1,001 and a half milliseconds, right? So that's about a second, right? A little bit longer due to who knows what, but that's the overall duration of that particular query. So by having the duration of the statement on the same line, we can go and find quickly statements and queries that took a long time to run. There is also a duration sample option, which you can use to log a sample of queries that exceed a given time rather than logging every single query that went over a certain amount of time, right? So here you would configure logmin duration sample, and then you can specify a sample rate, right? And so what that means is that you can actually get a lower number in terms of the overall time for the query and not overwhelm your system with a lot of logging. So something to be aware of is that if you enable logging for every single query, that means every single query is resulting in a write. That write is going into the logging system and is then having to get logged out to the file system. That all takes time, right? On a high throughput system, that can actually create a backlog, right? And push back pressure against the overall system and slow the overall system down and actually give you performance headaches in its own right. So on a really, really high throughput system, you probably don't want to set logmin duration statement down at 0. You might set it to 100 milliseconds, right, maybe, or you might choose to make it something lower but then have a sample rate instead, right, and use logmin duration sample. When you are logging information, there's a lot of useful information that you want to log, and this is a log, the way you get that information is by using logline prefix. So this is an example, timestamp, process ID, things like that that are really useful. This is largely pulled out of kind of what PG Badger's kind of default expectation is. Now, PG Badger is actually pretty smart. It can figure out what your logline prefix is. So you don't have to use this, but I find it's a pretty good logline prefix to use. I'll also upload this slide deck to the conference website after the end of, at some point after the end of this talk. Maybe not right after, but I'll try and get it up in the next couple of days so that you can take a look and see this. So here you can see a result of what that looks like with the user being sfrost, the database, the application client, etc. And you can see also this is the same kind of log duration statement as what I had before. The next item I'm going to talk about are checkpoints. So checkpoints are a process that's always running inside of Postgres, and what it's doing is it's taking dirty pages and writing them out and f-syncing them in particular so that in the event of a crash, we know we don't have to go that far back to replay, right? So it's able to move forward the point in the write-ahead log. The reason that this is relevant for slow queries is that large checkpoints, especially if they're happening very frequently, can again put that kind of back pressure on your overall system and make it so that your throughput is not what you want it to be. So I find it's very helpful to log information about checkpoints, and that's just log checkpoint on. And this is going to tell you when and why the checkpoint started, when the checkpoint completed, and a bunch of really useful statistics about the checkpoint itself. In particular, here you can see we have an immediate force wait checkpoint. This happened when you do something like a create database, right? This is another one where you can say, okay, well, if somebody goes and does a create database and it does a forced immediate wait checkpoint, that's going to create a huge I/O spike on your system, and maybe a cause for why queries, and particularly writing queries, ended up being a little bit slower, right? And so that's something that can be really relevant. You want to be able to kind of correlate between what was happening on the system when those slow queries happened and what other activity was going on. Other reasons why a checkpoint can start may be due to xlog, or wall, all right, depending on what version of Postgres. If you see a checkpoint happening due to xlog or wall, it means that your max wall size is not big enough to be able to store all of the information for that checkpoint in between the checkpoint timeout period. So if your max wall size is, 100 megabytes or a gigabyte or whatever, which is really small, and your checkpoint timeout is 5 minutes, well, you're probably going to write on a high throughput system more than a gigabyte in 5 minutes. Right, 5 minutes is a long time to be going. And you can generally write quite a bit of data in between those periods. But what that means is that we're going to be checkpointing much more frequently. And if we're checkpointing more frequently, again, that's going to have an impact on your query performance and on your system. Because checkpoints that happen more frequently are also going to tend to make your write-ahead log volume larger in terms of the amount of data you're writing, because we write what are called full-page images in between every checkpoint. And so every time you do a new page modification, that becomes a new full-page image inside of the write-ahead log. So if we're checkpointing every 10 seconds and you're updating 1,000 pages every 10 seconds, you're going to be doing 1,000 times 8K every second or every 10 seconds. That's a lot, right? Increase your max wall size, and that's going to help a lot. I always find it useful to log information about connections and disconnections. Another common thing I've seen, and where this can be really helpful, is if you're seeing a lot of connections and disconnections happening very, very quickly, that's going to reduce the performance of a Postgres system. There's a lot of setup work, and there are some per process caches that Postgres has that it has to populate whenever a backend starts. So if a new process is starting up because it's a new connection to Postgres, that first few queries along that connection are going to take longer. Because what is Postgres doing? It's populating the cache, okay, of information. There's a couple of caches. There's a sys cache and a relation cache, right? So literally in the back end of every Postgres process is a cache about every single table or object in the system that that particular backend has touched. And that means every time you're accessing a new relation from a particular backend, there's going to be some amount of work that Postgres has to do to read the information out of the Postgres catalogs and cache that information. So that's another reason why queries can end up being slow, is because we're having to populate that cache every time. So this is another case of like, if you're seeing that happening because you're logging connections and disconnections, you're seeing a lot of this happening, you should be like, okay, I need to go use a connection pooler. I strongly recommend something like PG Bouncer. That's certainly my favorite, but at least some kind of application level connection pooling can really help in that case. As I mentioned before, logging of lock weights is really, really helpful to be able to figure out, was my query slow because it was waiting on a lock? If somebody comes in and wants to add a column to a table, for example, that action is going to take out an access exclusive lock against that table for the period of time required to add the column. If there are other queries running on the system and trying to access that table, they're going to end up getting blocked behind that access exclusive attempt to add a column. In modern versions of Postgres, if you are just adding a column with a static default value, or if the column is nullable, adding of the column itself is very fast, but we have to get that lock first. And as soon as we attempt to do that alter table, anything that comes after is going to block waiting for that alter table, and the alter table is going to block behind any ongoing transaction that is accessing that table. So this is another reason why queries can end up seeming to be slow. Maybe it's not slow, it's just waiting on a lock. Log lock waits is ridiculously helpful in this case, because the way Postgres works is we have what's called a deadlock detector. The deadlock detector fires 1 second by default. It's based on deadlock timeout after a query has been waiting on a lock. So you start your transaction, you run a query, or you run an alter table, or whatever. That process then realizes that something else is blocking it. Something else has a lock that conflicts with the lock that we want. We're then going to go to sleep for deadlock timeout amount of time. And if the other process happens to finish, it'll notify us, right, saying, okay, I'm done, you can have the lock. We'll wake up and move on. If, however, after deadlock timeout hits, we have not acquired the lock, Postgres will run a deadlock detector just to make sure there isn't any deadlock in the system that Postgres can detect at least. Mind you, there can be deadlocks in the system that Postgres can't detect if your application is doing locking as well. So if you're doing any kind of locking, I strongly recommend you do all locking through the database. However, where this becomes really helpful is that as part of that deadlock detector, Postgres also will, if you enable log lock waits, dump out a bunch of information about waiting on that lock. It'll tell you information such as what process it was that was waiting, what kind of lock it was we were waiting on, who was holding that lock, and any other processes that were also blocking inside of the lock queue for that particular lock. And this is really, really helpful for figuring out like why a particular query might have been slow. Now, you're only going to get this after that deadlock timeout. So this isn't helpful, unfortunately, for cases where you're having slow queries that are only taking, they're slow because they're 200, 300, 400 milliseconds, right? In those cases, the deadlock detector will not have fired and you won't see that lock wait. You could possibly lower deadlock timeout in order to catch those cases, which I have done in some cases, but there's a trade-off there because running the deadlock detector is not cheap. And you don't really want to run the deadlock detector if you don't have to. Unfortunately, there's no way to like segregate those two things today. And you may or may not want to. Logging of temp files. Temp files are a good indication that for whatever reason, Postgres has had to spill over and start using temporary files to run your query. And if we're having to do a large, maybe on-disk sort because workmem isn't big enough, that's a great example of a case where logging of temp files will become, that will show that essentially, and that'll be helpful to figure out, okay, this is a query I need to go look at, and maybe I can do something like increase workmem. or perhaps rewrite the query in another way. The value is just whatever the minimum size is to log. So smaller amounts of temp files won't get logged. 0 means that it'll log all temp files. I like setting it to 0, but that tends to generate a little bit more logging than most people like. So setting it to something like 4 megabytes is pretty reasonable, which is the default for work mem. This is what that ends up looking like here. So here you can see we have a file that ended up being, 1 megabyte, but point being is that you see the file size, you see the temp file, and then you actually see this statement. So here you can see this select star from T1, order by 1. This is obviously a sort that's happening on disk, and that's where we're ending up having to use temp files. Logging auto vacuum activity is also a good thing to do because logging of auto vacuum activity, again, provides you that correlation for other activity on the system. So if there's other activity happening on the system, such as an automatic vacuum of a table, having auto vacuum min duration set to 0 will log that information, and you can go see was some kind of auto vacuum or happening at the same time that my queries were happening. And in the event that that's happening, that may be a reason why your queries were going perhaps a little bit slower than you like. So that's a lot about how to identify slow queries using logging. What are you going to do with that, though? Well, one of the things that you can do with that is once you've got all of this information in your log files, you can run a tool such as PGBadger and generate some really fancy reports with it. So I like talking through some of the reports that PGBadger shows. Let me see if I can bring this. OK. So here is an example of a PGBadger report where we have queries, number of queries, query duration, right? And this is all information that PGBadger has pulled out of the Postgres log file that we had it analyze for us. So these are examples of global stats. Here you can see they've got some, I really hate the resolution here. It's really driving me crazy. But here you can see SQL traffic. You can see maximum, minimum, average for queries per second. So that can be really helpful for seeing when there's a lot of load. You can have that split out by select queries versus insert, update, and delete queries. You can see query duration over time. And as you can see, if you hover over these things, you can see a lot of useful information about these queries. You can also see things like checkpoints. So again, you have to have enabled log checkpoints in order to get this information. But if you have, then you'll see this kind of useful information about checkpoints, how many buffers, like how big was each checkpoint, for example. Again, temp files is very similar. Vacuum locks, so here you can see locks, and you can see which queries were most frequently waiting on locks. And then another nice thing in here is that you can go and see actual examples, right, of particular cases in the log files where PGBadger found these cases. And then you can see specific times and go in and kind of drill down and see more information about a particular case that you are interested in. You can see what queries weighted the most. Obviously, these are all copy statements. Naturally, they're blocking behind each other, I would think. So that's just kind of a quick thing by looking through PGBadger. It also has the ability to get information out of PGBouncer log files. So in the event that you are using PGBouncer for your connection pooling, you can have PGBadger also analyze those log files for you too, and pull out useful information, byte throughput, query, average duration of queries, lots and lots of useful information. All right, so that's PGBadger. Let's see if I can, look at that. It's like I've done this before. Okay, so the next thing I wanted to talk about a little bit is understanding why some of these queries are slow, right? And that's a more complicated discussion, but I want it to be kind of the bulk of what we talk about here. So first and foremost is Postgres configuration issues. Also things like dead tuples and bloat, or quite frequently the biggest thing is query plan, right? So first and foremost, we're going to talk through some of the Postgres configuration. Workmem is one of your biggest tools when thinking about how to get queries to perform better. And the reality is bigger is always better. The more work mem that you provide, the more Postgres is going to be able to do in memory inside of a given backend, and that's generally going to help with performance. Not necessarily always, but very, very frequently. So that's something that you really want to consider. Maintenance work mem is helpful for speeding up things like index creation. Effective cache size. This is something that's going to encourage Postgres to do more index scans, and we'll talk about another one here in a minute that'll do that. So that's something else to think about increasing. Shared buffers. This is the big pool of memory that Postgres uses. In older sessions, I would have argued to make this too big, but Postgres has really gotten better at being able to work with larger amounts of memory. So a lot of people will set this to half of the memory in the system, and then go from there and tune it. A colleague of mine has a couple of really great blog posts about shared buffers and how to size shared buffers. So if you're interested, Keith Fisk, and he has two big blog posts about basically when shared buffers is too big and when shared buffers is too small. So things to look at. Min and max wall size, as I mentioned before, max wall size is a really important parameter because it controls how frequently checkpoints are happening, and so that may be something you want to look at. Checkpoint completion target, if you haven't tuned this yet on systems older than 14, I recommend going and tuning it. In 14, we actually changed the default for checkpoint completion target to 0.9, and that's really what I would recommend because that gives Postgres the entire checkpoint timeout in order to complete the checkpoint. Actually changing checkpoint timeout is another thing to consider to reduce the number of checkpoints that you have. The default is 5 minutes, which is a pretty good amount of time, but I've certainly seen systems that benefit from upping that to 20 minutes or 30 minutes. The downside of that, of course, is that in the event of a crash, you have that much more write-ahead log to replay. So dead tuples and bloat is another case where you can run into performance issues. And just to kind of highlight the way this works, in Postgres, everything is a insert and a delete, right? And an update is actually implemented as an insert and a delete. What happens is, therefore, the delete is only marking that record as deleted. It doesn't actually remove that record. And this is what creates bloat. And that happens inside of both the index and the actual heap. So you can have index level bloat, and you can also have heap level bloat. Vacuum is what goes through and marks those records as reusable, right? So reusable tuples, right, are space that we can actually go and put a new record. And you want to do that because you'd much rather reuse that space than have to extend a relation. Another case where you can end up with slow queries is particularly on inserts, right, on a heavy write load system. If you're having to constantly have the table be extended, right, and that means that there's no free space inside of the table, and we're having to constantly expand the table, which means going out to the operating system and asking for more disk space, that's a relatively expensive operation. More modern versions of Postgres have gotten a little bit better about this, in that if we detect that there are multiple processes all trying to get the extension lock at the same time, we'll actually extend out multiple blocks at a time. So this is better in more modern versions of Postgres, but it's still something to be aware of. And you really want to try and reuse tuples when you can inside of the heap because that avoids having to go deal with any kind of extension lock, and it's just cheaper because then we don't have to talk to the OS at all. In terms of any dead space that exists inside of the table, when we're doing something like a sequential scan, or if there's cases where there's a lot of additional entries in the index that we have to then scan through, right, we have to go consider those tuples, right? And that's not cheap. That's not going to be free for us to do that, and that can end up also leading to slower queries. More typically when you're pulling out large chunks of data and when you're doing sequential scans. That's when bloat becomes primarily an issue. If what you're doing are directed individual row lookups, then bloat is usually not that big a deal in those cases. There is a really useful utility, also written by my colleague Keith Fisk, called PG bloat check, which helps identify tables to go look at for bloat. And kind of as I was getting at, some bloat's actually useful, right? Having some free space means that we don't have to extend the table, and that's helpful. In order to eliminate all bloat, you have to actually rewrite the entire table, and that kind of stinks, right? If you are rewriting the entire table, that's going to be expensive. But there are a couple of ways to do that. Cluster is one, and vacuum full is the other. In both cases, basically what Postgres is going to do is scan the existing table and create a whole new table out of it, and then kind of flip-flop it into place for you. That whole process means that we are going to use a lot more disk space. So I don't really recommend these as a way of trying to get back disk space if you're close to the edge, right? If you're close to the edge, these are going to end up creating a lot of space or taking up a lot of space and may run you out of disk space. So be a little bit careful when you're using these. There are a couple of different ways of analyzing plans. So explain output has some different options. You can get it as XML, JSON, and YAML. And there are a couple of different tools out there for analyzing explain. PGadmin 3 and 4 have a pretty explain plan viewer. My favorite, however, is explain.depez.com. And this is the point where I always like to go show off explain.depez. I wish it looked a little bit nicer. I'm sorry that the resolution on here is not as good as I would like it to be. Hopefully you can at least kind of understand what's happening here. But for example, this is just a random query that I picked. So if we go to this history page, if I can find the button, there we go. You can see that there's a whole history here of lots of different explain plans. And you can just kind of click on one and say, oh, look at this. This is what this particular query was doing. And here, for example, you can see that this had a sort that was happening. This was doing an in-memory quick sort, right? So this is 137 kilobytes. And here you can see exclusive versus inclusive. So inclusive here means that this node plus all the other nodes took this amount of time. Exclusive means that this node took a certain amount of time. So in this particular case, you might be looking at the sort and being like, well, that sort is expensive because sorts are expensive. Well, in this case, it took, less than a millisecond, so it's not that bad, right? I think we're okay with that sort. So where would you want to look for to figure out where all the time went? You want to come down here and find, aha, so this one is another one, and here, but we really want to find if there's any kind of smoking gun in the, oh man, this is a big plan. And I can't see it all because I can't, all right. So here's some examples, right? So here's a hash left join. The actual hash left join didn't end up taking too much time, as you can see here, but inclusive, it did take some time. So here's one, all right, 283 milliseconds. And down here, 461 milliseconds. Those are some interesting numbers. We can say, okay, this had a materialize associated with it, with a left join underneath. So this is a merge left join. And a merge left join is going to end up needing to have some sorted data on each side. And you can see here, here's a good example, right? Rows removed by join filter. This is the one to look out for, right? If you're seeing a lot of things being filtered out, either by a join filter or by a regular filter clause, those are things where you want to say, okay, is there some way I could change this to allow it to have a index-based lookup rather than having to do a scan that's ending up having to do some kind of filtering. So yeah, here's another one. Yeah, rows removed by filter 14,000, right? So here we have a filter. This is a sequential scan. Maybe this is an opportunity to create an index. Now this particular table doesn't look very big, and Postgres is going to care about that, but that's the kind of thing you want to look out for, right? And this is where really I find that explain.depez is really, really helpful for being able to help you identify these particular cases where you can find where all the time's going and hopefully be able to address a lot of that time. So very, very useful tool for doing analysis. So here's, 1.4 seconds. So this is a big sort, right? So this is actually having to go out to disk too. When you see something like an external merge, right, from a sort, what that means is that Postgres ended up going out to disk to do this sort because we didn't have enough amount of memory available to us in order to do that in memory. Going out to disk, while we're not actually syncing that disk, is still more expensive than doing an in-memory sort. So if we, for example, in this particular case, increased work mem, we could maybe get this sort at least to become a quick sort and be done in memory rather than being done out on disk. And that could be helpful and could improve the performance. So this is another case that's, well, still not that interesting. Well, so we had to scan through over 30,000 records, right, as part of this sequential scan to pull out just the 234 that we actually wanted, because most likely there wasn't an index on this establishment ID column. Something to consider, right? Maybe we should create an index there as an example. All right, so I'm going to move back to talking kind of more generally about queries, but I'm always happy to come back to explain that to Pez if folks have questions about it. All right, so fixing slow queries. So similar to what I was just talking about, in the event you have something like a sequential scan, you have only a few rows being returned and it's not due to aggregation, that's an opportunity for creating an index, right? Other opportunities for creating indexes, one of the things that's really neat about Postgres, and it's not the only database that can do this, but Postgres has the ability to do what's called a bitmap index scan, right, and a bitmap heap scan. And what this means is that Postgres can actually leverage independent indexes to solve queries. So if you have an index on column A and an index on column B, and you have a query that says where A equals 5 and B equals 6, Postgres can actually scan both of those indexes, build up a bitmap of cases that it finds where A equals 5 and B equals 6 or whatever it is, and with that bitmap then do what's called a bitmap heap scan or a skipping scan through the table, right? So it's going to be able to actually just go to those specific records where both of those cases were true. This is another case, however, where workmem is really, really relevant. Because, for example, so what happens is if the bitmap ends up being too big, and this is something that you can see in your explain plans, it'll actually tell you in a bitmap heap scan how much of the bitmap was exact, meaning that we actually tracked down the page and the tuple, and how many cases were lossy. If you're seeing lossy in your bitmap heap scans, what that means is that the bitmap was too large to fit in workmem amount of memory, and Postgres started to reduce the resolution of that bitmap. When we reduce the resolution of the bitmap, we no longer are able to detect cases where the actual, we're no longer able to detect cases where the two tuples were on the same row, right? Maybe they were just on the same page. What do I mean by that? Well, if what we're tracking in the bitmap, it starts out always as the full tuple ID, that is the page and the individual tuple on that page. But when we have to reduce the resolution of the bitmap, we may reduce it all the way down to a page level, which means all we know is some tuple on a given page had A equals 5, and some other tuple on that page had B equals 6. But in order for us to go figure out if there was a tuple that satisfied both conditionals, we have to actually go pull that page and scan the entire page, and that's what the recheck condition is doing. So when you see a bitmap heap scan with a recheck condition, what that recheck is doing is checking to make sure that it actually matches the conditional that was requested, so that when we return that tuple, it's actually properly answering your query. So if you're seeing bitmap heap scans with lossy, you want to think about increasing workmem, right? Again, increasing workmem is going to be really, really helpful for that. So other cases where if you have like a small data set and you're seeing sorting or merge joins, this is another case where you may want to increase workmem. So this is more relevant in older versions of Postgres, but it used to be that Postgres, it used to be that Postgres was, Postgres' hashtag would only ever be used. So a hash aggregate is when we build a big hash table up in memory, and then we use that to do the aggregation. Well, it used to be that we would only do that in cases where we thought we could fit the entire hash table into workmem amount of memory. More modern versions of Postgres, I think this was 13 that this got implemented, 13 or 14, we actually started doing batching hashtag. So batching is another case where you want to look at and say, well, if batching is happening, either for a hash join, that we've had batching hash join around for a long time, but also for batching hash joins, we may want to increase work mem. Or hashags, we want to increase work mem. In older versions of Postgres, we wouldn't even try to do a hashtag if work mem didn't seem like it was big enough. So what we would end up doing is we'd do a grouping ag, right? A grouping ag is like a merge join, requires the data set be sorted. So this is what I'm talking about here. If you're seeing a merge join or you're seeing a group aggregate with a sort, it might be because Postgres doesn't think there's enough memory available to us to do a hash join, or there would have to be too many batches for it to be as efficient to do a hash join or a hash ag. Again, you want to increase work mem in those cases. In the event that you are seeing things like a large data set with a nested loop, sometimes this can happen due to statistics not being updated, right? In particular, when you do an explain analyze and you're seeing the row estimate, the number of rows that Postgres thinks we're going to get back at a given node, and the actual number of rows that we're getting back from that node being way off, especially at the lower levels like index scans and sequential scans, that's going to be an indication that our stats are off. And by a large difference, I'm saying orders of magnitude kind of difference, right? If you're seeing like we estimated 1,000 rows and we actually got back 1,200, that's probably fine, right? But if we estimated 100 rows and we got back 1,000,000, that's a problem. Right? That's a case where you want to make sure you go and analyze. Another case that's really interesting is if you have deletes and you have foreign keys involved, unlike some other database systems, Postgres does not require an index on the referring table. Right? And that means that when you delete something from the parent table, right, from the referred to table, right, Postgres is going to have to do a sequential scan to make sure that there isn't any entry in that other table referencing the row that we want to remove. And that can be really, really slow. So if you're seeing that, you definitely want to go create indexes on your referring side. You may want to do that anyway. If you are ever using foreign keys with cascades, you probably want to go make sure that the referring side has indexes on it so that we can go look those up quickly. Prepared queries, of course, can be helpful for avoiding repeated planning cost. This is something that you may want to consider using if you're not already. There's upsides and downsides. Postgres actually has this notion of generic and specific plans, and it'll kind of try and flip-flop back and forth between them. But just in general, you want to think about using plan once and run many if you have that opportunity. Here's an example of how you can also get an explain analyze out of a prepared query. So this is a case where you may see things with like an ORM or something, and you're like, the query is slow, and then you take that query and run it by hand, and it's fast. Sometimes that can be because you gave Postgres more information by doing that, by letting it have all of the constants as part of it, right? Instead, you probably want to do a prepare similar to how the ORM or your application level is doing it, and then use explain analyze on the execute so that you're mimicking it similarly. If you're seeing, if you're doing like a lot of count stars, this is actually something that people don't always realize. An index can help, right? Because you can do an index-only scan. However, we still have to go check all the records, which means we have to scan through the entire index. So it's still not going to be free. But selecting of count star can be helped by having an index. Note, however, if you have cases where you are expecting an index-only scan to happen and you're not seeing that happen, you may want to go vacuum that table. Postgres depends on the visibility map being up to date and accurate, and that visibility map is maintained by vacuum. So if the table isn't getting vacuumed or isn't getting vacuumed frequently enough, the visibility map may be out of date, and that can have an impact on your performance because those queries that maybe were using an index-only scan might stop using it because the visibility map has become out of date. If you're doing like large select stars, you always want to go back and say, do you actually need every row or every column? In particular, large values with Postgres will be toasted. That means they'll be stored out of line in a side table. Any individual value over 2K is Postgres is going to try and compress. We'll also store it out of line if we aren't able to fit it on the page. and that means storing it in a side table. If you're pulling back a 10 megabyte or even 10 kilobyte piece of data and you don't need it, that's expensive and you're wasting time. Also watch out for select distincts. Maybe you're just really missing a join clause. I was recently dealing with this because some tool created a query that had a select distinct that was completely unnecessary, right? That distinct is going to imply a lot of times a sort and a unique node. Those are expensive. You want to avoid that if you can. Make sure that you are actually having all of your join conditions. And in particular, I recommend using join syntax rather than doing comma joins like the initial query. So I also say avoid using large in lists. And I say avoid using large in lists with subselects and with actual values. As it turns out, if you use a large value set for an in list, the parser is actually not that fast at that, right? Because it's a generic Postgres parser. Use an array instead, right? Pass an actual array into Postgres. The array parsing is a lot faster. So something to consider. Also, don't use not in. This also ends up being a little bit slow, and in many cases we can't prove that we could turn that into an anti-join. What we really should be using here is either a left join or a not exists, because those are going to allow us to do an anti-join in Postgres, which will be able to do like a hash-based join, and that can be a lot faster. This is not as relevant, but used to be we always materialized CTEs on older versions of Postgres. On more modern versions of Postgres, we don't do that unless you explicitly ask for it. So I still generally feel like CTEs are something that you probably want to not have be like, have a lot of stuff coming through, but it's not as big a deal anymore. You can also use a faster estimate. If you just need an estimate for how many tuples are in a table, you can just query pgclass.rel tuples. It's only useful for whole tables, and it won't be perfect, but it is an approach that you can use. So in terms of tuning Postgres, you want to increase work mem, increase maintenance work mem, set effective cache size based on the amount of memory you have, increase shared buffers. Partial and functional indexes are really helpful. If you haven't used those before, I highly recommend considering them, because you can create an index over just part of a table, or you can create an index over top of the results of a function. Do always make sure that you double check your query plans and make sure that your query plans are actually using the indexes that you create, especially if they are partial or functional indexes. Sometimes casting and other things can make it be difficult for Postgres to be able to prove that using that index is the right thing to do. So you want to make sure that you're actually checking that. Also, unused indexes have to be maintained, so you always want to make sure that you only have the indexes defined that you're actually using. So if you have a lot of indexes, your writing queries are going to end up potentially being slower due to that. And if you're not actually using those indexes, either for constraint proofs or for, say, actually using them as part of the queries, then you're just wasting a lot of time updating those indexes for not much benefit. So you can review the table called pgstat user indexes to see if indeed those indexes are being used, and if they're not, you may want to consider dropping them. And with that, I believe I have a few minutes left to be able to answer any questions that folks have. 5 minutes left, so I've got lots of time. Yes?
So,
oh, use the mic, use the mic.
I know we were recording this. So PG Badger's pretty nice.
Yes. Sorry, pgstat statements. I don't know what happened to my slides on those. I had slides on those, but I also ran out of time, so it's fine.
pgstat statements really useful too.
If you want to look at active
More
queries, definitely use pgstat statements, and that'll give you things like minimum time, maximum time of ongoing running queries in the system, rather than doing it with PG Badger. Sorry, go ahead.
No, that's what I was going to get to. So PG Badger is really nice looking for retrospectives, right? So like you can go and look at what happened before. It would be really awesome if log, statement, log, locks, all of those things were output in a way that could be consumed, for example, by Prometheus, where you could get linear predictions or something like that. It says the rate of the average of this particular query has been going up over time.
So that is
and
the
I'm
way
letting you know before your application crashes that it's going to happen, right? Via PagerDuty or whatever.
The way to do that analysis is with pgstat statements, and people already do that today, right? Use Prometheus to scrape pgstat statements. Inside of pgstat statements is a query ID. You can pull that query ID out, and that's generally going to be stable for a given query, at least through a given Postgres major version. So you can use that as your identifier in your Prometheus system as an ongoing review of, ongoing statistics for that particular query.
So with PG Monitor, for example,
Yes.
it could be, but if that had all the capabilities of PG Badger, then it would be like that much more powerful, right? Like if you could get all of this pushed to you as it's happening, or
more and
predictions.
more of it is being made available. So more and more of what's in the log. So log checkpoints is a good example, right? You see that in the log files, but now we also have that information inside of stat tables as well. You can see when a checkpoint, you can see how long checkpoints have been taking to happen, how much buffers were written, things like that are now also available through some of the other PG stat views. So we are getting there. We're making improvements in that area. I'll also point out something I thought you were going to ask for, but something that is also being worked on currently in community that's hopefully, knock on wood, going to make it into 15, is the ability to ask for what the current query plan is for the running query, right? Yeah, so that's something that's being worked on currently, is to be able to send a signal to that backend that says, hey, dump out your query plan for me, which would be really cool, right? That would be really neat to be able to see what that is. Today, you can't really do that. You can only see it kind of after the fact. You can't actually be sure that you see the same exact query plan as what the query plan is actually running. You can just do another explain and hope that the stats haven't changed that much, which is not a guarantee. Other questions? No. I think everybody's just tired, and it's Friday afternoon at 4 p.m. I can't say I blame anybody for that. No other questions?
Sounds good. Well, thank you, Stephen.
Awesome. Well, thank you, everyone.